If a macrostate is realized by n microstates, the information in bits needed to encode this microstate is the logarithm of n, okay? So if we just look at a base 2 number system and a system of spin-up, spin-down particles, then if we have n particles, we need n pieces of information to encode the microstate. Namely, we encode the microstate by specifying a 1 or a 0 for each particle, depending on whether it's in the spin-up or spin-down position. However, the total number of microstates is actually 2 to the power n. So you can see that the information needed to encode the microstate scales logarithmically with the number of microstates. We call this quantity the informational entropy. Now, if to each microstate we associate a uniform probability of 1 over n, and the information required in bits to calculate or to code the microstate is negative log p, because remember, log n is this amount of information required to encode the microstate, and so log n is precisely log 1 over p, or negative log p, okay? So now, if we take p to be an arbitrary probability distribution, not just a uniform probability distribution, then the entropy is the expected value with respect to this probability distribution of microstates of the informational entropy associated with each microstate, okay? And so this is where you derive the entropy functional in optimal transport theory. Or just is more general than optimal transport, obviously. But in application to optimal transport theory, if you let X be a Polish space, so a separable complete metric space, and P of X the space of probability measures on X, then via the theory of optimal transport, there's a metric called the Wasserstein metric, W2, on the probability space. And if we consider the entropy functional, which takes a probability measure and maps it to the expectation value of its informational entropy, the expectation value with respect to this probability distribution of the informational entropy associated with each microstate of the system. So this is calculating the total energy of the system given by this probability distribution over the space of microstates. Then this entropy functional actually has a gradient flow structure with respect to the Wasserstein metric, okay? So this entropy functional has a gradient flow structure with respect to the Wasserstein metric. And what is that gradient flow structure? Well, if I start with initial density rho naught, then the maximizing movement curve, so the maximizing movement curve, which basically moves, is an absolutely continuous curve in the probability space with initial value rho naught, and it moves in the direction of steepest increase of the entropy functional, is precisely the curve given by essentially the heat equation, okay? So when you apply the heat equation in time to your initial density rho naught, that is actually the path which maximizes the entropy, okay? So we have a fundamental connection between the heat equation that you might learn in a PDE course and actually a maximizing movement of the entropy functional. But this connection can only be built with the metric structure provided by optimal transport in this Wasserstein distance. Without this metric, there are other functionals whose gradient flow is the heat equation, but they're more of a vertical measure of they're with respect to a metric. They're with respect to a metric which is more of a vertical measure of distance between the probability distributions. Whereas, so like if I had two Gaussians, I'd be integrating, for example, the total variation norm. If I take two Gaussians and I integrate their pointwise difference of their densities, that absolute value, the pointwise difference of their densities with respect to the little Beck measure, I integrate that over the entire space, and that's going to give me the total variation norm, but that's more of a vertical notion of distance. It doesn't capture the horizontal notion of distance between probability measures. On the other hand, the Wasserstein distance does capture this horizontal distance between probability measures, okay? And so traditionally you'll see that the Dirichlet energy, if you take like a course on partial differential equations, you'll see that the Dirichlet energy is the gradient flow of the Dirichlet energy is the heat equation with respect to the L2 norm. So so with respect to the L2 norm, the gradient flow of the Dirichlet energy is the heat equation, okay? But again, this is saying that that the heat equation somehow works to destroy like local vertical displacements in heat, and basically forces local equilibrium to be established, basically by minimizing this integral of the grad of the function squared, which is the Dirichlet energy. But the entropy functional, turns out that in order to get the entropy functional as the functional whose gradient flows the heat equation, you actually need to turn to the Wasserstein metric, which gives you a notion of horizontal distance between probability measures. So yeah, I thought this was pretty cool, and I just wanted to share that. And also, I'm going to come back to this video and review it for my own sake.